So we're going to wrap up chapter 15 by looking at principles of metabolic regulation. This is a survey, so we're looking at regulation in biological systems. We're looking at glycolysis versus gluconeogenesis, and we're looking at chemistry and the regulation of glycogen metabolism. So we know that pathways have a dedicated purpose, so the extraction of energy or the storage of fuels, or the synthesis of important building blocks, and sometimes the elimination of waste materials. So these pathways can be represented as a map. You can actually follow the fates of metabolites and building blocks. You can identify the enzymes that then act on those metabolites, and you can look at points of regulation, and sometimes you can even identify sources of metabolic disease. Obviously, right, metabolic pathways can be incredibly complex. So if you think about it in terms of a three-dimensional network, really what you're looking for here are the intersection points. So where are the overlaps, where are the points of junction or diversion? And so that's really what we're looking for. And again, you could find some of these in exquisite detail in terms of categorizing the metabolic, say for example, human metabolism. If we look at homeostasis, we know that organisms maintain homeostasis by keeping the concentrations of metabolites at a steady state. So in a steady state, the rate of synthesis of a metabolite equals the rate of breakdown of that metabolite. And so we can make the assumption that pathways are always at steady state unless they're perturbed. And after a perturbation, a new steady state will then be established. And so it's really the flow of metabolites through the pathways that's regulated to maintain homeostasis. And so sometimes the levels of required metabolites must be altered very quickly. So that's the need to increase the capacity of glycolysis, or the need to reduce the capacity of glycolysis, or the need to increase gluconeogenesis after successful action. So there are ways in which we can uptick or downtick depending upon need. In most cases, the ultimate products of metabolic pathways directly or indirectly inhibit their own biosynthetic pathways. So ATP, for example, inhibits the commitment steps of glycolysis. So if I have a lot of ATP, then I'm not going to be going through glycolysis. If I look at the rates of biochemical reactions, these are going to be dependent upon many factors. So the concentration of reactants versus products, the activity of the catalyst, the concentration of the enzyme itself, the rate of translation versus the rate of degradation of that enzyme, the intrinsic activity of the enzyme. That could depend on substrate, that could depend on effectors, the phosphorylation state, and then the concentrations of effectors. So here we're talking about things like allosteric regulators, competing substrates, pH or the ionic environment, and then of course there's also the role of temperature. When you're looking at factors that determine the activity of enzymes, we're really looking at the number of molecules that are in the cell or its effective activity in a subcellular compartment, or the ability to modulate activity of existing molecules. I could combine these factors to influence the rate at which enzymes have activity. So this rate of reaction really depends fundamentally on the concentration of substrate. So the rate is more sensitive to concentration at low concentrations. So that's dependent upon the frequency of a substrate meeting with the enzyme. And then the rate becomes more insensitive at higher substrate concentrations, largely because the enzyme is nearly saturated with the substrate. We can actually see this when we look at a saturation curve, where we look at initial velocity, and we look at ATP concentration. You're familiar with these because we use them to convert the saturation curves into the Michaelis-Menten plots. But this idea of Vmax and 1/2 Vmax, and really being able to determine the substrate concentration at that rate. So many enzymes have a Km that is near or greater than physiological concentration of their substrate, especially those that utilize ATP or NADH. If I look at the phosphorylation of enzymes and the way that affects their activity, so phosphorylation is catalyzed by protein kinases, dephosphorylation is catalyzed by protein phosphatases, or it can also be spontaneous. And so typically proteins that are phosphorylated are on the hydroxyl groups of serine, threonine, or tyrosine. If I look at enzymes that are regulated by regulatory proteins, this is the binding of a protein subunit that affects specificity. So you can think of these almost as gatekeepers. And then the last piece is that proteins have a finite lifespan. So different proteins in the same tissue can have very different half-lives. So less than an hour a week for liver enzymes. That stability correlates with the sequence really observed at the N-terminus. And then some proteins are actually as old as you are. So for example, the crystallins in the lens of your eye. So if you look at the average half-life of proteins in mammalian tissues, you can actually see for kidney, those are 1.7 in terms of days. For the heart, 4.1. For muscle, 10.7. Reactions that are far from equilibrium are common points of regulation. So within a metabolic pathway, most reactions operate near equilibrium. Key enzymes operate far from equilibrium. So these are the sites of regulation. They control the flow through the pathway. And again, to maintain steady state, all enzymes operate at the same rate. If we take a look at table 15-3, these are the equilibrium constants, mass action coefficients, and free energy changes for enzymes of carbohydrate metabolism. These you could obviously use to interconvert and solve for the other. So we'll stop there and we'll pick it up for part 2. Thanks again.